Assalamu alaikum and welcome to lecture number 7. In this lecture we are going to talk about the impulse invariance, continuous time processing of discrete time signals, and downsampling. In the previous lecture we have talked about the processing of continuous time signal using discrete time system. As shown in this figure. So we said that the cascade system of this figure is equivalent to an LTI system for the case of band limited input signals. In this case we assume two constraints, that is equation A and equation B. We said H of Ej omega, a discrete time system response, equal to HCj omega by T when omega absolute is less than pi. Similarly, the second constraint was that the response is 0 for absolute of omega is equal to or greater than pi by t. So using these relations we can find the relationship between the continuous time impulse response HCT and discrete time impulse response Hn by the equation C, which is shown here. So you can say that similar to converting a continuous time signal XCT. So when we convert XCT continuous time signal into discrete one, we find that we have scaling by 1 by t, and we have replicas of the original signal around 2 pi. So similar to converting a continuous time signal into discrete time, the response of the system. So the response of the discrete time system is basically a scaled and sampled version of continuous time system impulse response. When the Hn and HCT are related by this equation, the discrete time system is said to be an impulse invariant version of the continuous time system. So I hope you understand. If you think about the signal, so for the signal we also had similar relationship. So we obtain the impulse invariant version of the continuous time system using this equation, and simply it says that H of n is scaled and sampled version of the HCT. You understand HCT is the impulse response of the LTI system, right? So for the LTI system having impulse response HCT, C you understand means for continuous time, right? So in this course we'll use HC or HA, both means the analog or continuous time signal, right? So this is the equation that relates the two responses, that responses of the discrete time and the continuous time system, and they are related by this equation. So this is called the impulse invariant version of the continuous time system. So hope this gives you idea, because we have done the part on the in detail about the sampling of the continuous time signal. So when we sample the continuous time signal, you understand we get scaled and shifted version of the continuous time signal, which have multiple copies or replicas around 2 pi. So let's consider an example. So the information provided is that we have a ideal low pass discrete time filter, and the discrete time filter has cutoff frequency omega c, which is less than pi. So we can do by sampling a continuous time ideal low pass filter with a cutoff frequency omega c equals to omega c by t. So you understand that's also the relationship between the continuous time signal frequency and discrete time signal, or the frequency of the system. So cutoff frequency is omega c, and this is related to the continuous time by the omega c equals to uh, omega c of the discrete time system divided by the sampling interval. And the condition must be met, this one, that the cutoff frequency is less than pi by t. So hcj omega is equal to 1 for absolute omega is less than omega c, and it is equal to 0 otherwise. So the impulse response of this continuous time system is hct equals to sine of omega ct by pi of t, right? So you understand how we get this value. Basically, this is your frequency response, right? So taking the inverse Fourier transform, right? This is continuous, so taking the inverse Fourier transform or continuous time Fourier transform, we will get impulse response, which is this one. So using the impulse invariant equation, we can find the impulse response of the discrete time system. In this particular case, low pass filter. So this is the impulse response for the continuous time system. Now the impulse response of the discrete time system and continuous time system, they are related by impulse invariant equation, which says that h of n equals to t times the hcnt, right? This we done on the previous slide. So by putting the value, we can obtain the impulse response of the equivalent discrete time low pass filter, which is this one. Okay, simply omega c into t. You understand the relationship between the frequency of the continuous time signal and the discrete time signal, which is this one, that we say omega c equals to omega capital omega c times t. So this is the relationship between continuous time signal frequency or the system frequency and discrete time. Okay, so using this equation, we can replace omega c into t by omega small omega c. So we can write this sine of small omega c into n, right? And because this t cancels with this one, so you get the equivalent response for the low pass filter in discrete time is this one. So the desired frequency response in the is given by this equation, which is simply the Fourier transform of this one. Okay, taking Fourier transform of this one will result into this, and we have h of ej omega, which is frequency response of the discrete time low pass filter, equals to 1 when omega absolute is less than cutoff frequency and 0 otherwise. The next topic we are going to consider is the continuous time processing of discrete time signals, right? So previously we have done the topic that is discrete time processing of continuous time signal. In that case, the input signal was continuous and the system was discrete. So what we did, we converted the continuous time signal into the discrete time signal. Then we processed using the discrete time system, and after processing, we converted the signal again to continuous time by discrete to continuous reconstruction. Now in this case, we have continuous time system and we have discrete time signal. So what we will do, the first step will be that we convert the discrete time signal into the continuous time signal, and I hope you understand we use the reconstruction or interpolation to convert a discrete time signal into a continuous time signal. So by doing this, we get the continuous version of the input signal. Then we have continuous time system, which is HCT. That is, HCT is the impulse response. You understand impulse response is in time domain, whereas the equivalent frequency response is represented by hcj omega. So you understand C here signifies that the system is continuous. So once the input signal is given to a continuous LTI system, we obtain the output signal, which is YCT, and because the desired signal is discrete, so again we will convert this continuous time into discrete time so that we obtain the desired result, which is discrete time, right? So your input signal is discrete time and your output signal is also discrete time because your system is continuous. So what you do, you convert the input signal which is discrete into a continuous signal, process it using continuous time system, and then you convert the signal back to the discrete time, so you obtain the output signal y of n. So from the definition of the ideal discrete to continuous converter, the input signal xcj omega and the output signal ycj omega must also be band limited. So that means their frequency, that is for the frequency absolute of omega equal to or greater than pi by t, these two signals will be 0. So you understand that basically this equation relates the Nyquist criteria. So based on Nyquist criteria, your maximum frequency, twice of the maximum frequency, must be less than the this is the Nyquist criteria, that the maximum frequency present in the signal, 2 times of it should be less than the sampling frequency. You understand sampling frequency and sampling period. Sampling frequency we represent by omega s and the sampling period by t. So the relationship between them is this is equal to 2 pi, right? So that means omega s equals to 2 pi by capital T. So we can write like this, or we can also write instead of this one, we just say okay, 2 times omega n must be less than or equal to 2 pi by capital T. Remember that capital T is sampling period. Okay, so 2 cancels with 2, so we get the relationship. So that means for positive or negative frequencies, that means omega n should be less than pi by t. So that means for the omega greater than or equal to pi by t, these two signals must be 0, so that we can ideally convert them from discrete to continuous without aliasing, because if this condition is not met, then we'll have aliasing. You understand what is aliasing? These are the equations for the ideal discrete to continuous converter, right? So that's the impulse response of the ideal low pass filter or reconstruction filter. Okay, and that's your input x and t, right? So here we have input x and t. So using this equation, we first convert it into a continuous time, right? And again, that's your yct, and this is equal to y of n, which is discrete time, and multiply by the ideal low pass filter, so that we can convert it into a continuous time. I hope this gives you idea. If you have any question, you can ask in the live session. So I think many of the parts you have already done. Discrete to continuous converter you have already done when we were doing the sampling and reconstruction. So again, here continuous to digital converter, so that you have this part you have also done. So I hope by now it gives you clear understanding of what you're doing for the converting discrete time into continuous time, or continuous time into discrete time. So the frequency relationships are we have the continuous time signal which we obtain here. So this is your discrete to continuous converter. You understand, in case of discrete to continuous conversion, we use a filter with gain t. So the continuous time signal will be equal to t times the discrete time version which you have here. Okay, and this is band limited, okay, satisfying the Nyquist criteria, and we represent it by, we give it a name, equation D. Similarly, the output signal which you obtain here, ycj omega, equals to the input signal which is xcj omega, this one xcj omega, and multiplied by the frequency response here which is hcj omega. So the output signal we obtain is ycj omega, which is equal to xcj omega hcj omega times the input signal which is xcj omega. Okay, and we give it name equation E. Similarly, the reconstructed signal here will be equal to y of j omega, y of ej omega. You understand, ej omega signifies the discrete time, right, frequency response. So that is the discrete time Fourier transform. Okay, so y of ej omega equals to, this is your signal which you obtain here. Now once you convert this signal from continuous to discrete domain, so this is basically scaling it by a factor of 1 by t. So this will be equal to 1 by t and yc, and for j omega we write, because the capital omega, the relationship between the capital omega and the small omega, you understand, small omega is the discrete time signal frequency, capital omega is the continuous time signal frequency. So capital small sorry, let me write the expression here. Okay, I think by now you must know. Anyway, I write again. So capital omega, which is the frequency of the continuous time signal, times the sampling period, equals to omega c, which is the frequency of the discrete time signal. So that means capital omega basically equals to small omega divided by the sampling interval or sampling time or sampling period. Okay, so that's omega by t. So because we are reconstructing it, we are converting it to discrete domain. That's, it's already continuous. So we, right, this continuous signal, we are converting it from continuous to discrete. So you understand how we convert the from continuous to discrete, we sample it, right? Those things you have done already. So straight away I write, okay, we get, because here the scaling factor will be 1 by t. Okay, so the output signal we obtain here, which is y of j omega, this will be equal to 1 by t times the omega, right? You understand, if you recall that we have after sampling, what we get. So after sampling we get this thing, this equation. I hope you are familiar with it. This is your x of ej omega equals to 1 by t summation k running from minus infinity up to infinity, xc j omega by capital T minus 2 pi k by t, right? Now with the this constraint that omega is less than pi, that means we exclude this term and the summation will be over. We will have just xcj omega by t, right? If we use this constraint that the input signal cannot have frequency greater than pi. So this we have done for the signal x, right? Now we have the signal yct, that's continuous time signal. So x is replaced with y, so we'll have the, it's a Fourier frequency domain representation. So we'll just write, instead of x of c, we will have y of c, and all the replicas are removed. We only keep omega by t. So we have this, okay, and this is your scaling factor. So I hope this gives you idea. So that's your y of ej omega, that is the signal you obtained after converting the continuous time into a discrete time. Okay, so that's the signal you get here. right? So I hope you understand how you get this one. This was your this is your input signal. So when you convert the input signal, which is discrete, into continuous one, you get this equation. Okay, now this is your continuous time signal, and this continuous time signal goes through the system. The system has frequency response HCJ omega, so that means you are in frequency domain, so you just multiply the signal with the response to get the output signal, right? So I just multiplied XCJ omega with HCJ omega, right, to obtain Y of CJ omega. Now after that we are converting it from continuous to discrete. So it's simply, if you recall this expression, and in this expression we have to limit the frequency. The frequency cannot be greater than pi. It must always be whether absolute of this must be less than pi. That means frequency will be less than minus pi, right? If you let me plot this also, for example, we have, right, so I have plotted the signal here. So I hope you understand what this absolute symbol means, although you have done multiple times in signal and systems. So again, so that means you are limiting the output signal YC j omega by t to this frequency range. So that means, for example, this is the omegas, right? So this is the limit of the frequency. So that means if this is the limit of these frequencies, then this simply reduces to omega by t. Okay, so this will be, and because you are just using this one, so all summation is removed, and you just get 1 by t xc j omega by t. In this particular case, this is y of t, so it will be we can just say y of e j omega equals to 1 by t y c j omega by t. So hope you understand, right? So this is how you get this final, right? So the final output is basically the input signal times the not this is the response, this one, right? This is the frequency response. So your output is frequency response times the input signals. Here you get this signal which is continuous in nature. So now to convert this into a discrete time, you have this constraint. So based on this constraint, you can just say y of e j omega will be equal to 1 by t y of c j omega by t, right? So I hope you got idea. You get this from here, right? Because that's the generalized expression for continuous to discrete to continuous time. Okay. So that means the overall system behaves as a discrete time system because input is discrete and output is also discrete. So this here the block diagram. Inside block diagram, whatever is happening, but the overall response of this block diagram is that you have this frequency response. Okay. So for example, we say that h of e j omega is the frequency response of this overall system if the frequency of the continuous time signal, right? So in all cases, remember that we are assuming that the Nyquist criteria is met and signals are band limited, right? So that means x of c j omega equals to 0 for this frequency range. Okay, so for the inside of this range, it has some value, but outside of this range it is 0. So HCJ omega may be chosen arbitrarily above pi by t, right? So again, you understand that's the from the Nyquist criteria. A convenient but arbitrary choice for HCJ omega, which is the frequency response of the continuous time system, this one, is that it is equal to 0 for the frequencies outside the Nyquist range. So I hope this gives you some idea. So from here onwards, we start a new topic, that is changing the sampling rate. Changing means that we can upsample or we can do the downsample. You know, we have different formats for audio. For example, we have a compact disc or CD, and the data there has sampling rate of 44.1 kilohertz. Similarly, we have another format, that is digital audio tab, and digital audio tab has sampling rate of 8 kilohertz, and the another one is the digital telephony, which has a standard that is called the pulse code modulation, or PCM, and PCM uses sampling rate of 8 kilohertz. So sometimes we required to convert from one sampling rate to the other one, right? So you understand that definitely it will affect the quality of the data, but it is requirement that sometimes we need to, for example, you send some audio data, maybe CD data on a digital telephony. So digital telephony hardware has the sampling rate of 8 kilohertz. So in digital telephony, you can understand the highest possible frequency will be, because we have sampling frequency. You understand the 8 kilohertz means you are using the linear frequency. You're talking about the linear frequency. So you can convert from linear to angular frequency. Simply the relationship is 2 pi into linear frequency basically equals to the angular frequency, which is represented by omega. So if you talk about the linear frequency, so in case of linear frequency, the maximum frequency, for example, we have Fn. So 2 times Fn should be the Nyquist criteria is the sampling frequency, that is let it represent by Fs. So Fs should be equal to or greater than 2 times this one, right? So that's in terms of the linear frequency. So because we have the sampling frequency here 8 kilohertz, so that means the 8 kilohertz we have the sampling frequency. So that means 8 kilohertz, right, equals to 2 times F maximum frequency, which we represent by Fn. So that means the maximum frequency possible with the standard telephony is 4 kilohertz, which is very low. So that I hope you understand, if you listen to the voice on or music on the telephone and the same music on some other thing, for example on computer, so you can tell the difference between the quality of the two. So anyway, we have these different formats and we have to change, right? So upsampler and downsampler are the basic elements used in multi-rate system for sampling rate conversions, right? So depending upon, if for example telephony standard speech is to be recorded on CD, then we have to upsample it, or the CD is going to be transmitted on telephone, then we have to downsample it. So upsampler and downsampler are the basic elements used in multi-rate systems for sampling rate conversion. So to understand the process of up or down sampling, consider an analog signal XAT, right? So I hope you understand that we are using XAT for analog signal, or similarly we can also use XCT for the analog signal. So these will be interchangeably used, but they both mean the same. XAT means analog signal, XCT means continuous signal, so they both mean the same. Okay, so we have XAT, analog signal, which is sampled with sampling interval of TS. Also TS or the capital T, they are also same, right? So just S here signifies that it's a sampling period, but even if it is not written, it is just written T, so that T means the sampling interval or sampling period. Okay, so we have sampling period this one, and we convert this analog signal XAT into the discrete one. So this is the simple relation. I hope this is clear to you because you have done this so many times. Okay, So sampling frequency equals to this relationship. I hope that's also clear to you, right? The relationship between the frequency and the time is that in case of linear frequency, you have this relationship, that is t and f are reciprocal of each other, so t equals to 1 by f. Now if we multiply this both side by 2 pi, then we get not this 2 pi. In fact, if I divide by 2 pi, right? So if I divide both sides by 2 pi, then this 2 pi f, this will become radian frequency, and radian frequency, angular frequency, sorry, which has units of radian per second. So now if I cross multiply, so this and this, so you understand that omega, we denote the frequency by omega. Okay, so that's capital omega to represents the continuous time signal frequency. Okay, so that means we have if we cross multiply, so t into omega equals to 2 pi, right? So that's the equation. So given one, you can find the other one. Okay, so that's a relationship. We have discrete time signal equals to x of analog sampled at interval is in an interval of ts seconds. So the sampling frequency will be equal to omega s equals to 2 pi by ts, right? So we assume that xat is band limited and it has maximum frequency of omega s by 2. So again, that means it is satisfying the Nyquist criteria that the maximum frequency it contains is the half of the sampling frequency. That's what the Nyquist criteria says, that it should be less than or equal to half. So here we see that it's omega s by 2, so that it is meeting the condition, right? So you understand when the maximum frequency in any signal is less than half of the sampling frequency, then that means there will be no aliasing. Okay, for example, the original signal xat is no longer available. Okay, and we have sampled it and we got the discrete time version of this signal. Okay, and now we want a new set of samples x dash n taken with sampling period t dash s, and t dash s is not equal to ts. Okay, so that means we want to change the sampling frequency, or we are changing the sampling interval, right? So the new samples are related to the previous one as x dash n equals to xa n ts dash n. So if you want to do this, because we no longer have analog signal, so how should we get the new samples? Because now we want a different sampling frequency or different sampling rate. So definitely the generated signal will be different, that is x dash n will be different from x of n. So how we can do this? Okay, so the easy one is that we reconstruct the discrete time signal. That means we convert the discrete time signal back to the analog signal, and after that we sample it with our desired sampling frequency. But this is very expensive in terms of that we need to make a circuit that will take the input as xn, and it will produce its analog version, and then once you get the analog or the continuous version, you sample it with your own desired sampling rate. So a better option will be that we do this all in digital way. That means we sample we obtain x dash of n from x of n. downsampling. In downsampling, we want a new set of samples represented as x prime of n or x dash of n taken with a slower sampling frequency, that is ts prime equals to m times ts, right? So that means ts prime is greater than ts, so that means we will have fewer samples than previously we were getting. So in terms of frequency, we can write that omega prime s equals to 2 pi by t prime s, right? So that's a relationship, standard relationship. You understand that omega s into t equals to 2 pi, or you say that omega s equals to 2 pi by t. So if prime here, prime is also here, right? Now because ts is equal to sorry, ts prime is equal to mts. So if I write m and then ts, so that means the omega dash s will be downsampled version, right? How much? Omega dash s will be equal to omega s divided by let me write it again. So omega prime s equals to 2 pi by t prime s. Now t prime s basically equals to mts. So that means we can write 2 pi by mts. Now 2 pi by ts is basically omega s. So that means I can write omega prime s equals to omega s divided by m. So now you can say that the sampling frequency has been reduced by a factor of m. Previously it was omega s, now it's omega s by m. So it is reduced by a factor of m. So we can say that the new sampling interval is m times longer than the old sampling interval, or equivalently the new sampling frequency is m times slower, right? From this equation, I hope this gives you idea, than the old sampling frequency. So that means x prime n equals to xa n ts n prime ts. Now t prime s is basically mts, so that means the new signal will be equal to the analog signal sampled at this time interval. Okay, so that means x prime n is downsampled version of x of n, which we can write as x prime of n equals to x n m right, and x n m equals to x of analog n mts. So that means this is the relationship between the new new means the downsampled version of the discrete time signal, right? So a device that does this is called a downsampler, or it is also called compressor, as shown in this figure, right? So we have input x of n, we downsample it by a factor of m, so we get x prime of n, which is equal to, with the original signal, this is equal to x of n m. Okay, so m samples we are throwing away. The original signal has the sampling interval of Ts, whereas the new one has the sampling interval represented by T prime S, and it is equal to MTS. Hence, the number of samples in the output or in the new signal are reduced by a factor of M, as it should be, because the sampling rate is also decreased by the factor M. So with this we end the lecture for today, and we'll start the next lecture from this slide. Okay, Allah Hafiz.